Hello, everybody. My name is Tasia Morioka, and my teammates are Anna, Amy, and Becky. And today's lesson is going to be on diffusion's temperature dependence. What is diffusion? Diffusion is basically the random Brownian movement of molecules from high concentration to low concentration. If you haven't learned about it yet, you're going to need to know it for your high school biology, chemistry, physics. It's going to be in all of that, but it's just a very important principle for everyday life because it governs a lot of biological and chemical systems that are occurring in your body, in everyday activities like cooking. Diffusion is everywhere. Understanding how factors such as temperature could influence diffusion is very fundamental to understanding the concept of diffusion as a whole. To begin our experiment, here are the materials we used. Here's our solute, solvent, our hot plate and ice pack were used to adjust the temperatures of our solutions that are held in a flat dish, and we use a thermometer to keep track of it.
Now I'm going to go into the procedure and setup for our experiment. We wanted to test a wide range of temperatures, so we had three different setups. For the hot temperature range of 80 degrees Fahrenheit or higher, we set the dish on top of a hot plate, which will heat up the liquid to the desired temperature. For the room temperature ranging between 45 to 80 degrees Fahrenheit, we set the dish on top of the table and nothing else was adjusted to its surrounding. For the cold temperature, we ice the water in a separate container and set the dish on top of an ice pack. Now, the purpose of these three variations was to keep the temperature as constant as possible throughout our experiment. Once the setup is complete, we record the temperature of the water with a thermometer, and when ready, we drop the Skittle into the water and start the timer. Here's a side-by-side comparison of the diffusion at the three temperature. At the top right here, we have the hot temperature, and you can see just how fast the dye comes off of the Skittle. On the bottom here is our room temperature, and you see that the dye is diffusing slower than the hot temperature, but faster than the cold temperature, which is on the top left. Now we're stopping the timer exactly at the point of which the dye crosses the circle that we drew here. And that is how we are measuring exactly how fast the rate of diffusion is.
So now we'll be discussing and analyzing the results from our experiment. Looking at the table on the left, you can see that we held 9 trials at 3 different temperature ranges. At colder temperatures, the dye from the Skittle took more time to diffuse the set amount than the trials held at room temperature. The trials held at higher temperatures took less time for the dye to diffuse than, again, the trials at room temperature. And this can be visually represented by the graph on the right, where you can see the general trend line of the time it took for the dye to diffuse as we increase the temperature. You may also notice that there is some variance within the trend line, which can be explained by human error within our experiment. For example, the table may have been slightly tilted, causing one side of the Skittle to diffuse further. And also the fact that it was very difficult to keep the temperature constant the entire experiment. It also caused variance within trials. And finally, the fact that Skittles are not all shaped and sized exactly the same. And these all can contribute to the slight variances within the trend lines.
There are three main equations we are considering when looking at diffusion in our experiment. The first is Stokes-Einstein equation. This equation describes a solid diffusing into a liquid. When considering this equation, we can see that as temperature increases, so does the diffusive coefficient. We can also use two different versions of Fick's law to model our experiment. In the first version, we can cancel out the convective term because we can assume that the solution was dilute. This is due to the amount of water compared to the amount of dye from the Skittle. We can also cancel out the convective term in the second form of Fick's law due to the fact that there was no overall bulk flow velocity. Both of these equations ultimately simplify to this form of Fick's law. And overall, we can see that as temperature increases, we can see that the diffusive coefficient also increases, which increases the overall amount of flux or diffusion that occurs. By increasing the temperature of the system, energy is being added to the system. On a molecular level, the energy of each individual molecule increases. The energy of a particle dictates the amount of random motion it exhibits, also known as Brownian motion. As temperature increases, the velocity at which the particle travels increases, increasing the overall rate of diffusion, which is what we found in our experiment.
Understanding the relationship between diffusion and temperature is very important for chemical engineers, as we are the ones who manage the synthetic systems that are dependent on these diffusive concepts. So I hope that you learned a lot today so that you too can put this skill on your LinkedIn. Thank you.